All right, so let's go to 6.3. 6.3, we are on definite integrals and antiderivatives. Okay, and 6.2, we talked about definite integrals, so we are kind of familiar with that. So let's kind of look at the properties of definite integrals. So if you look at page 293, the bottom of page 293, there is a table that says rules for definite integrals. Okay, so let's talk about these. So we have, first we have, if we went from here, f of x, d of x, as you can see here, because we're going from A to A, okay, there is no area under the curve. Obviously that would be 0, correct? Because you're at the same point, there's nothing going on there, right? And then we have the additive, which is nothing more than if I go from A to B, and then I go from B to C, and this will be the same as from A to C, right? So if I go from A, B, and C, A, B, and C, A to B would be this guy here, B to C would be this guy here, which is the same as from A to C, okay? Nothing miraculous there. Order of integrations. So this is kind of interesting. This is the same as the negative of B to A dx, okay? If you think about it, it makes sense, right? If I move this over, I'm going to get this plus this is equal to 0. A to B to A, right? Obviously, it's going to be the same as A to A, which is 0, correct? Okay. And then we have the constant multiple. Constant multiple is that if there is a multiple here, if there is a k here, I can pull that k out, and this is the same as that. So I can pull the k out, and this will be the same as that, because it's just a constant, right? And then we have sum and difference. If I have A to B, and I go from f of x, and I have f of x plus or minus g of x dx. This is the same as A to B, f of x dx plus or minus A to B, g of x dx. Okay? So the sum or the difference just becomes the difference here, the sum or the difference here. Okay? That is 6. And then we have 7. That was 5. I'm sorry, that was 5. Okay, now let's talk about 6. 6 is a little interesting. It talks about the max value and the min equality. So if we have max and min, so if I have a function, it looks like this, and I'm going from A to B, okay? The area under the curve here is going to be, so A to B f of x dx is going to be smaller than the max value A to B. So what is the max value here? What is the max value between A to B? The max value is going to be right here, correct, for f of x? So if you look at the area under the curve there, it's going to be this rectangle, right? This rectangle here, the area of this rectangle. So the area under this curve is going to be smaller than that rectangle. And this is going to be the min. So if we look at the min, so that if I have the min A to B f of x dx, it's going to be this guy right here, right? It's going to be this guy right here. And this guy's going to be smaller than the area under the curve from here to here. That makes sense. Everybody understand that? Are we good with that? Okay. And then we have domination. Domination kind of makes sense. If f of x is greater than g of x in all throughout the entire part that we're talking about, this is f of x, and we'll call this g of x, right? As you can see, from A to B, f of x is always going to be greater than g of x here, within A to B, right? So the area under the curve from A to B for f of x is always going to be greater than that of g of x. So if within A to B, okay, in that boundary, so we can say that A to B, f of x dx is A to B g of x dx, because it's dominated, it's always greater throughout the entire A to B. Okay? All right, so that's that. Let's go to example number 1 and see if we can utilize some of these things that we just learned, some of the rules, and see if we can do example 1. Example 1, suppose that from -1 to 1, f of x is dx is equal to 5, 1 to 4, f of x dx is equal to -2, and from -1 to 1, they're calling it h of x here, h of x dx is equal to 7. Okay, let's do A. A says, what is 4 to 1 f of x dx? What would that be? We know this one right here, right? So this is more than just nothing more than switching the boundaries, right? So what do we get? We get the negative of this value, right? 2. Then we have B, which is -1 to 4 f of x dx. And this is the same from here to here, and here to here, just added together. So that would be 3. And then we have C, which is -1 to 1. Let's do C. -1 to 1, we have 2 f of x plus 3 h of x dx. So how do we do this? How do we approach this? Christina, how would I do this?
Bring the 2 and 3 in front of the not derivative, some multiple the.
So you would go ahead and separate the two first, right?
Oh yeah, separate 2.
Well, that's oversight.
-1, 1, 3 h of x dx, right? This is the first thing we would do. And then I'm going to pull the 2 up front. I'm going to pull the 3 out also.
Okay.
Right?
Yeah.
Now I know what this is. What is this?
And that is multiple 5 multiple by 5.
Yeah, so it'll be 5.
Oh yeah,
right?
by 2. Yeah.
Over here we have 3 times.
Would not agree with that.
And
That's
7,
all right.
yeah.
So, all right. Well, I'll follow that advice, and I appreciate your candor
sorry.
again.
3, 10 plus 21, which would be 31, correct? Okay. So we'd have 31. That would be 31. Okay, D, 0 to 1 f of x dx. So in D, 0 to 1 f of x dx. What would this be? Logan, what would this be?
But
Huh?
yeah, what'd you say?
D, 0 to 1, f of x dx. What is that? Based upon what we know here.
I have no clue.
No clue. Okay, that is actually the correct answer because there is no way to find that out, right? I know that it's from 0 to 1 is 5, but 0 to 1, I have no information, right? I don't know. It's, you know, we can't say it's half of this. We don't know that, right? So we don't have enough, we do not have enough information here to figure this out. So we do not know this. Okay, so we do not know this.
Wow, Logan is so smart.
E, we have negative 2 to 2 h of x dx. So as far as h of x knows, we know this right here, right? From negative 1 to 1, it's 7. But again, we have no data between negative 2 and 2. So this is the same thing. We do not know. Okay. F, we have negative 1 to 4, f of x plus h of x dx. Okay. So the first thing again we would do, we would separate these, right? So it would be negative 1 to 4, f of x dx plus negative 1 to 4, h of x dx. Right? So from here to, from negative 1 to 4, we already did that. That was 5 minus 2. So this guy's going to be 3. We know that is 3, right? From negative 1 to 1. And then from 1 to 4 is negative 2. So it's 5. Negative 2 is 3. Over here, what can I do about this? What do I know here? Do I know enough?
No.
No. What do I need to know? What is the missing piece that I don't have that prevents me from solving this part?
What h of x is between -1 and 4?
Well, more specifically, I know what it is from negative 1 to 1, right? I don't know what it is from 1 to 4. That's the piece that we're missing, correct? Right? Again, so we do not know this, okay? We do not know this. We do not have enough information. Okay? Good. Let's go to example number 2. Example number 2, show that the value is less than that. So f of 0 from integral from here, 0 to 1 plus cosine x dx. And I want to show that this is less than that. Okay? So we do not know how to do this yet. Okay, we have not learned enough to do this. Okay. But what would be the maximum value of cosine x?
1.
1. Okay, are we sure about that? Let's look at this. Cosine x goes like this, right? 0 to pi over 2. So 1 is greater than or less than pi over 2. Anybody? JJ.
I don't know.
What is pi? (3.14/2), right? So it's going to be 1.507, something like that, right? So obviously 1 is going to be over here, so it'd be less than that, right? So from here to here, the max value obviously is going to be 1. So the maximum this guy can be is going to be that. Can we see that? Right? Let's say that for argument's sake that it was 1 all the way across from 0 to 1. Okay? Then I get this, which is 0 to 1 square root of 2 dx. Now this is a constant, right? This is a constant. So this is going to be equal to the square root of 2 from 1 to 0. So the most that this could ever be is going to be square root of 2. Right? Can we see that? So now let's compare square root of 2 and 1.5. What is square root of 2?
Like 1.4 or something?
1.414, right? So therefore, this guy is always going to be smaller than 3 over 2. Everybody see that? Are we good? All right? Okay. Okay. Average value of a function. This is a new definition for you guys. Now we are going to define the average value of a function between A and B. Okay, if you go to page 295, it gives you that definition there, right? Average value, if f is integral between A and B, okay, we're going to say that the average value of f is going to be equal to b over a1, a to b, f of x dx. Okay, this is what we're going to call, this is the average value of the function. So let's look at this over here. This guy here is what? If this is A, and this is B, this is the area under this curve, correct? Area under this curve, and we're going to divide that by the width. And we're going to call that the average value, okay? So that's what we're talking about here, okay? So it could be anywhere here or wherever it may be, right? Wherever it may be, okay? So let's see if we can use that. Let's see if we can do example number 3. Use this definition. Find the average value of f of x of that on 0 to 3. So we need to find the average value of f of x, and we're going to go from where to where? Okay, so we're going to go b minus a over 1, a to b, f of x dx. So where are we going from here? From where to where?
0 to 3.
0 to 3? Oops.
Yep.
From 0 to 3. So this is going to be 3 over here. 3 minus 0. And what was f of x?
4 minus x squared.
Dx. Right? So this will be 1/3 of 0 to 3, 4 minus x squared d of x. Let me write that again. Okay. We still don't know how to do this. Since I don't know how to do this, what would I do, Sam?
Plug it into the calculator.
No, so let's do FNINT. Let's go to our calculator and see if we can do FNINT. What do we get?
3.
3. Everybody else get 3? Are we good with the 3? Everybody know how to use this, do this on their calculator by now, I hope. All right? So the average value is going to be 1. All right? And then we come to the mean value theorem for definite integrals. Okay, we had the mean value theorem, and then we had the mean value theorem for derivatives. Now we're going to talk about the mean value theorem for definite integrals. Okay. So the mean value theorem for definite integrals is going to look like on page 296. It says if f is continuous on a to b, then at some point c, you're going to have something that is going to look like this. You're going to have a C value where when you multiply it times this guy, or it's going to be the same as, what was this? Anybody remember what this was?
The average.
The average value, right? So at some point you're going to have a C where it's going to be the same as the average value. Okay, and that's what they're saying. All right. Okay, blah, blah, blah. Okay, we're going to save the last for the next half. So let's go ahead and we can get started working on our homework.